Welcome to the deep dive. Ever look at a map and just wonder what's going on miles and miles beneath your feet?
Oh, absolutely.
Today, we're embarking on an incredible journey, really, to the Earth's hidden depths. Forget just the surface, we're going all the way down.
That's right. Think of this as your ultimate backstage pass to our planet. We're using the chapter from Earth, Portrait of a Planet, the 6th edition, as our guide.
And we're not just skimming.
No way.
Yeah.
We're diving deep into the core geology, the powerful processes at play, and even how this hidden world impacts our everyday lives.
Exactly. We walk around on what feels like solid ground, but underneath is this dynamic, constantly shifting realm. Our mission today is to make sense of this unseen universe for you.
Uncovering some truly mind-bending insights along the way.
Yeah, and we'll even tackle those diagrams that sometimes look a bit like abstract art and figure out what they're actually telling us.
Okay, so to get us started, even with our earliest understanding, we kind of knew the Earth had a layered structure a bit like an onion, right?
Right, the classic model.
Based on its overall mass and shape, scientists figured out 3 main zones: the crust, the mantle, and the core. That basic division is shown really nicely in one of the early figures in the chapter.
That's the picture most of us remember from school, yeah. But when you think about actually seeing what's down there, it hits you how limited we are.
Total.
The deepest we've ever dug with a mine is, what, a tiny scratch? About 3.9 kilometers?
Something like that, yeah. And the deepest drill hole, still only 12.3 kilometers.
It's like trying to understand the Grand Canyon by, I don't know, looking at a single pebble.
Exactly. It's nothing, really. So to truly explore Earth's interior, we've had to become clever detectives, relying on indirect clues.
Geophysics.
Geophysics, exactly. Our main tools are studying the behavior of seismic waves, those vibrations from earthquakes, measuring the subtle variations in gravity, and analyzing the Earth's magnetic field. These are our remote sensors giving us a peek into the unknown.
Okay, let's unpack the first set of clues then. Seismic waves. These vibrations, mostly from earthquakes, are like the Earth's natural ultrasound, right?
That's a great analogy. They spread out from the earthquake's source in expanding wave fronts, and we track these using imaginary lines called seismic rays.
What's fascinating, you mentioned, is that these waves change speed depending on what they're traveling through.
Yeah, just like sound travels faster in water than in air.
Yeah.
The velocity of seismic waves is affected by the material's density, how tightly packed it is, its rigidity, how stiff it is, and its compressibility, how easy it is to squeeze.
And the book gives a great example. A P wave, that's one type of seismic wave.
Compressional ones, yeah.
It ambles through sandstone at maybe 3.5 kilometers per second, but hit pteridotite, that dense mantle rock.
Whoosh. It speeds up to around 8 kilometers per second.
That difference is huge. It tells us something fundamental about what these layers are made of.
Exactly, and it's not just the type of rock, but also its state, solid or liquid. Seismic waves generally travel faster through solids. And there's a key difference between the 2 main types. P waves, the compressional ones, can travel through both solids and liquids. But S waves, the shear waves,
They need something solid to shake.
precisely, they can't travel through liquids. Imagine trying to shear water. You just can't do it.
Yeah.
And that becomes super important later on.
Okay, so waves change speed. And when they hit a boundary between different materials, they don't just keep going straight, right? They can bounce or bend.
Right. They can bounce back, which we call reflection, pretty straightforward, angle in equals, angle out. Or they can bend as they pass into the new material, which is refraction. And refraction is really informative.
How so?
Well, if a wave enters a slower material, it bends away from the boundary. If it enters a faster material, it bends towards the boundary. Think of it like light bending as it enters water.
Okay, yeah.
It's this bending, this refraction, that led to the first big discovery about Earth's layering, the Moho.
The Mohorovicic discontinuity. That's a mouthful.
Oh, yeah, usually just called the Moho. Back in 1909, Andrija Mohorovicic noticed something odd about P-wave arrival times after an earthquake.
What did he see?
He saw that P-waves traveling relatively short distances arrived at one speed. But waves that traveled farther away actually arrived sooner than you'd expect if they just stayed in that upper layer.
Wait, hang on. Longer distance, shorter travel time. How does that work?
That was the puzzle. His brilliant idea was that the closer waves were just traveling through the Earth's crust, a relatively slow layer.
Okay.
But the farther waves must have dipped down into a deeper, faster layer. The mantle bent at the boundary, sped through it, and then bent back up. Even with the extra depth, The higher speed in the mantle meant they won the race to the distant seismometers.
Ah, clever. So that boundary where they bend is the Moho.
Exactly, the base of the crust. His calculations put it at different depths, maybe 35 to 50 kilometers under continents, much shallower, 7 to 10 kilometers under oceans, and deeper under big mountains, up to 70 kilometers.
A fundamental division. But even within the crust itself, things aren't uniform. You mentioned waves travel faster in the lower continental crust.
That's what the data suggests, yeah. Lab experiments point towards the lower crust being more magnific, richer in denser minerals with magnesium and iron. Think dark volcanic rocks like basalt. Denser stuff usually means faster wave speeds.
Okay, makes sense. Now let's go deeper into the mantle. Seismic waves keep giving us clues. If the mantle was totally uniform, waves would just go straight, right?
Or curve gently due to pressure, yeah. But there's this specific zone, particularly clear beneath the oceans, between about 100 and 200 kilometers down, where P-wave velocity actually decreases.
A low velocity zone, or LVZ. What's slowing them down there?
The best explanation is partial melting.
Hmm.
The temperature and pressure conditions there cause a tiny amount, maybe just a few percent of the mantle rock peritite, to melt.
Just a little bit.
Just a little, yeah. But this tiny bit of liquid coats the solid grains, and since waves slow down in liquid, the overall velocity drops.
And this LVZ, that's basically the asthenosphere, the gooey layer the plates slide on.
It's the upper part of it, yes. That weak zone is crucial for plate tectonics. Interestingly, we don't see such a distinct, clear LVZ under the older, thicker parts of continents.
Huh. Okay. So below the LVZ and generally throughout the mantle, velocity increases with depth.
Right, because the pressure is just immense. It squeezes the rock, makes it stiffer, harder to compress, so the waves travel faster.
And this gradual increase in speed with depth is why the seismic raise curve as they travel long distances through the mantle.
Exactly. They're constantly bending slightly as they enter ever so slightly faster material deeper down, resulting in that curved path we see on diagrams.
Then we hit these sudden jumps in velocity, right? Around 410 kilometers and 660 kilometers deep. What are those about?
Those sharp increases aren't compositional changes, like the Moho. They're phase changes. The incredible pressure forces the atoms in the mantle minerals to rearrange themselves into denser crystal structures.
Like squeezing coal into a diamond, but with mantle minerals.
Sort of, yeah. Above 410 kilometers, the main mineral is olivine. At 410, it transforms into a denser structure, sometimes called wadsleyite or beta spinel. Then at 660 kilometers, that transforms again into even denser minerals like bridgmanite, which is a perovskite structure, and ferropericlase.
So the rock type is fundamentally the same, but its internal structure changes.
Pretty much. It's like the Earth is constantly reorganizing its internal building blocks under that extreme pressure.
And these jumps divide the mantle.
Correct. We talk about the upper mantle down to 660 kilometers and the lower mantle below 660 kilometers. That zone between 410 and 660, with all the rearranging happening, is called the transition zone.
How do we even know these specific minerals exist down there and transform like that? We can't exactly grab a sample.
Right. That's where things like diamond anvil experiments come in. Scientists take tiny bits of suspected mantle minerals, squeeze them between incredibly hard diamonds.
Recreating the pressure.
Exactly. They can hit pressures like those deep in the mantle. They can even zap them with lasers to get the right temperatures. By seeing how the minerals behave, how their structure changes, they can predict how seismic waves should travel through them.
And then compare that to what we actually measure from earthquakes.
And when the predictions match the observations, well, that gives us a lot of confidence that we're on the right track about what the mantle is made of.
Amazing. Okay, even deeper now. The core mantle boundary, another huge division. How was that found? Benno Gutenberg, you mentioned.
Yes, Benno Gutenberg, 1914. He discovered the P-wave shadow zone.
The what now?
He noticed that P-waves from earthquakes just disappeared. They weren't detected at seismometer stations located between about 103 and 143 degrees away from the earthquake's epicenter, measured around the curve of the Earth.
A whole zone of silence for P waves.
A shadow zone, yeah. If the Earth just get denser smoothly all the way down, the waves should arrive everywhere, maybe bent a bit. This shadow meant something drastic was happening deep inside.
Something bending the waves sharply downwards.
Exactly. It indicated a major boundary where the P-wave velocities suddenly decreased significantly, causing that sharp downward refraction. That boundary is the core mantle boundary, about 2,900 kilometers down. Waves that just skim it make it 103 degrees. Waves that dive in get bent so much they only reappear beyond 143 degrees.
Leaving that gap in between. Okay, but what about the core itself?
That came from studying the S waves. Seismologists found an even bigger shadow zone for S-waves. They don't arrive anywhere beyond 103 degrees from the epicenter.
And S-waves can't go through liquids.
Bingo. That was the smoking gun. The huge S-wave shadow zone meant the outer part of the core must be liquid, a vast sphere of molten metal.
Wow! Molten iron alloy, thousands of kilometers down. Just incredible. But wait, there's another twist, isn't there? An inner core.
Yes. Thanks to Inge Lehman in 1936. She was looking closely at seismograms and noticed some faint P-waves showing up within the P-wave shadow zone where they shouldn't have been.
How?
Her interpretation was that these P-waves had entered the liquid outer core, but then reflected off another boundary deeper inside.
A boundary within the core itself.
Exactly. She proposed the core wasn't entirely liquid, but had a solid inner core. Later work, especially using seismic waves from nuclear explosions, which give really clear signals, nailed down the depth of that inner core-outer core boundary at around 5,155 kilometers.
So liquid outer core, solid inner core, both mostly iron and nickel. Why the difference? Why is one liquid and the other solid if they're made of similar stuff?
It comes down to pressure and temperature. There's a great diagram showing the Earth's internal temperature gradient, the geotherm, and the melting curve for iron alloy under pressure.
Let me guess. In the outer core, the actual temperature is higher than the melting point at that pressure.
You got it. The geotherm is above the melting curve, so it's liquid.
But in the inner core,
The pressure is even higher, which raises the melting point of iron a lot. So much, in fact, that even though the inner core is incredibly hot, the melting temperature is even higher. The geotherm actually drops below the melting curve, right at the inner core boundary, so it stays solid.
fascinating balance of heat and pressure. That diagram also explains the partial melt in the LVZ too, right? Where the geotherm just kisses the melting curve for mantle rock.
Precisely. It's a really useful way to visualize why different layers are in different states.
Okay, so we've mapped out the layers using these waves, but the Earth isn't static, is it? The inside is moving. How do we picture that? Seismic tomography. Sounds like medical imaging.
It's very similar in principle. Like a CA-CAT scan uses X-rays to image inside the body, seismic tomography uses seismic waves to create 3D images of the Earth's interior.
How does it work?
Scientists compare the actual travel times of thousands, even millions, of seismic wave paths crisscrossing the Earth with the times they'd expect based on a simple average Earth model.
Okay.
If waves arrive faster than expected, it suggests they pass through regions that are cooler, denser, and more rigid than average.
Colder means faster.
Right. And if they arrive slower, it indicates warmer, less dense, more pliable areas.
Warmer means slower. And they use colors to map this. Blues for fast cold, reds for slow hot.
Generally, yes, that's the common convention. Blue blobs for cold, fast regions. Red blobs for hot, slow regions. And the images are stunning.
What have we learned from tomography? What did these blobs show us?
All sorts of incredible things. For instance, beneath North America and other places with ancient subduction zones, we see these large blue, fast regions extending deep into the mantle.
That's cold oceanic crust and lithosphere that sank down millions of years ago.
That's the interpretation, yeah. Slabs of old, cold plate that have plunged deep, sometimes even reaching the core mantle boundary. People talk about a slab graveyard down there.
Wow. And the red, warm blobs.
We see those under places like mid-ocean ridges and volcanic hotspots like Hawaii or Iceland. These slow zones clearly indicate areas where hot mantle material is rising up from below.
Supporting the idea of mantle plumes and upwelling driving plate tectonics.
Absolutely. Tomography also helped define the D layer, that zone, at the very base of the mantle, just above the core. It seems to be thermally and chemically distinct, maybe where mantle plumes originate, though that's still debated.
So tomography gives us this incredibly dynamic picture. It's not just static layers, it's full of these huge upwelling and downwelling currents, mantle convection.
Exactly. It visualizes the Earth's internal heat engine in action. And it's also changed how we think about subducting slabs. They're not just rigid sheets plunging down.
No.
They seem to behave more like very, very viscous fluids over geological time. They can fold, buckle, thin out, maybe even break apart as they sink through the mantle. Tomography shows us these complex shapes.
This technology keeps getting better too, right? Like the USRA project.
Oh, absolutely. EarthScope's USRA was this amazing experiment with a dense grid of seismometers moving across the United States.
Denser network means clearer pictures.
Much clearer, yeah. especially for the upper mantle and the crust right beneath our feet. It's giving us unprecedented detail about the roots of mountains, the structures beneath volcanoes, all sorts of things.
And seismic methods aren't just for deep Earth science. There's seismic reflection profiling used closer to the surface.
Definitely. That's a huge tool in geology and resource exploration. Instead of waiting for earthquakes, geologists use controlled sources like vibrating trucks or air guns offshore to send waves down.
And listen for the echoes.
Exactly. They record the reflections bouncing off different rock layers underground. By analyzing the timing and strength of these echoes, they can build up detailed pictures of the subsurface geology faults, sedimentary basins.
Which is crucial for finding oil and gas, or mapping groundwater resources, or understanding earthquake hazards.
Absolutely. And the techniques have advanced incredibly. They can now create full 3D seismic images, revealing incredibly complex buried structures like ancient river channels miles underground. It's amazing technology.
Okay, let's shift gears a bit. Seismic waves tell us about structure and state. What about gravity? How does that help us probe the interior?
Well, gravity, that fundamental force pulling everything together, depends on mass and distance. More mass, stronger pull. Closer distance, stronger pull. Yeah. We can think about gravitational potential energy. Something higher up has more potential to fall. And a key concept is the equipotential surface, a surface where the gravitational potential energy is the same everywhere. A perfectly still ocean surface would approximate this.
But the Earth isn't perfectly smooth, and its mass isn't perfectly evenly distributed, so its equipotential surface isn't a perfect sphere either.
Not at all. We use a reference shape, a slightly flattened sphere called a spheroid, to account for rotation. But the Earth's actual gravitational equipotential surface at sea level, the geoid, is irregular. It has bumps and dips.
Bumps where there's slightly more mass underneath, dips where there's slightly less.
Basically, yeah. The geoid undulates compared to the perfect spheroid. The highest point is about 85 meters above. The lowest is about 107 meters below. It reflects the uneven distribution of mass within the Earth mountains, deep trenches, variations in density in the crust and mantle.
And we measure these variations as gravity anomalies, differences from the expected smooth field.
Exactly. We use incredibly sensitive instruments called gravimeters to measure the precise strength of gravity at different locations. Where gravity is slightly stronger than expected for that latitude and elevation, that's a positive anomaly, suggests excess mass below.
Like a dense ore body, maybe?
Could be, yeah. That's one application. Where gravity is weaker, that's a negative anomaly, suggests a mass deficit, maybe less dense rocks like salt domes or thick sediments. So mapping these anomalies helps geologists understand subsurface structures and find resources.
The source then brings in Archimedes' principle, buoyancy. How does that apply to solid rock?
It applies to the concept of isostasy. It's the idea that the Earth's rigid outer layer, the lithosphere, is essentially floating in gravitational equilibrium on the more ductile, slowly flowing asthenosphere beneath it.
Like blocks of wood floating in water.
Exactly like that. Thicker blocks or less dense blocks float higher. So continents, which are made of thicker, less dense crust, stand higher than ocean basins, which have thinner, denser crust.
And mountains. They have deep roots pushing into the mantle to support their height.
That's the idea of isostatic compensation, yes. And the lithosphere adjusts vertically if you change the load on it. Put a giant ice sheet on top, it sinks down. Melt the ice sheet, it slowly rebounds back up.
Like parts of Scandinavia and Canada are still doing after the last ice age?
Precisely. Now, it's not always perfect equilibrium. The asthenosphere flows slowly, so adjustments take time. And the lithosphere has some strength. It can bridge over small areas or support temporary loads.
And these deviations from perfect isostasy can also show up as gravity anomalies.
They can. For instance, you often find negative gravity anomalies over deep ocean trenches because the strong, downgoing slab is holding the trench down deeper than it would naturally float. Young, rapidly rising mountains might have a positive anomaly if their buoyant root hasn't fully formed yet.
Okay, one last piece of the geophysical puzzle. Earth's magnetic field. We know it shields us. Acts like a giant bar magnet, roughly.
Roughly, yes. A dipole field with a north and south magnetic pole is a good first approximation.
But it can't be an actual giant magnet down there, right? It's way too hot.
Correct. The temperatures in the core are far above the Curie point, the temperature where materials lose their permanent magnetism. So the field has to be generated continuously.
By the movement of the liquid outer core? The dynamo effect.
Exactly. It's a self-exciting dynamo. You have this vast shell of churning, electrically conductive molten iron alloy. Its motion creates electrical currents.
And electrical currents create magnetic fields.
Right. And that generated magnetic field interacts with the moving fluid in a way that sustains and reinforces the field. It's a complex feedback loop.
And the Earth's rotation plays a big role, organizing the flow.
A huge role. The rotation and the Coriolis effect tend to organize the convection currents in the outer core into these large spiraling columns, roughly aligned with the rotation axis.
Like spinning weather systems, but made of liquid metal.
Kinda, yeah. And it's these organized spirals that are thought to generate the main dipole component of the Earth's field. Interestingly, this flow might also drag the solid inner core along slightly faster than the rest of the planet rotates.
Core superrotation. Heard about that. And what about magnetic reversals, when north becomes south?
That seems to be a consequence of the dynamo being somewhat unstable over long timescales. Those convective spirals can sometimes break down, become disorganized, and then reestablish themselves, but with the opposite polarity. Computer models can simulate this kind of behavior.
Wow. And just like gravity, the magnetic field isn't perfectly uniform either. We see magnetic anomalies.
Right. Two main causes. First, the dynamo isn't perfectly simple.
Hmm.
There's turbulence and complexity in the outer core flow that generates non-dipole parts of the field, causing regional variations.
Okay.
Second, and very importantly for geology, rocks in the crust can become magnetized. When igneous rocks cool below their Curie point, magnetic minerals within them, like magnetite, align with the Earth's field at that time and place, locking in a permanent magnetization.
Ah, like tiny compass needles frozen in the rock.
Exactly. And these magnetized rocks create their own local magnetic fields that add to or subtract from the main Earth field, creating magnetic anomalies we can measure at the surface.
Like the magnetic stripes on the ocean floor, recording the reversals over millions of years as the seafloor spread.
That's the classic example, yeah.
Mm.
On continents, the patterns are much more complex because you have all sorts of different rock types with different ages and magnetic properties matched together by tectonics.
So mapping these magnetic anomalies also helps decipher the geology beneath the surface.
It's another crucial tool in the geophysicist's toolkit.
So from the faintest whispers of seismic waves coming from the core, to the subtle pull of gravity, to the shifting magnetic field, we've really covered a lot about how we explore our planet's hidden interior.
We really have. These geophysical methods, these indirect clues, they give us this incredibly detailed, evolving picture of the Earth beneath our feet. Its layers, the dynamic processes like convection and phase changes, even things that help us find resources or understand hazards.
It truly underscores the immense complexity, doesn't it? And how interconnected everything is. What happens thousands of kilometers down really does influence our world up here on the surface.
Absolutely. And, despite everything we've learned, there are still huge mysteries.
Which leaves us with some big questions, I suppose, like what future secrets will techniques like seismic tomography uncover about the deepest mantle or the core itself?
Or how might changes in that churning outer core, the engine of our magnetic shield, affect the field in the future? And what would that mean for life on Earth? The Earth's interior is definitely still a frontier.
Well, that brings us to the end of this deep dive into Earth's interior, grounded in the interlude chapter of Earth, Portrait of a Planet. We've hit the core geology ideas, the key processes like convection and isostasy, tried to make sense of those diagrams.
Talked about real-world examples, the practical applications.
Yep, covered seismic waves in detail, the nuances of gravity and isostasy, and the whole fascinating story of the magnetic field and the dynamo. I think we've managed to explore pretty much all the key aspects presented in the chapter.
It's been a fascinating journey down there.
Definitely, a journey into the hidden realm beneath our feet.